Hello, welcome to the fifth lecture, fifth video of this course, and let me start with a correction which was in last video. I made the mistake. It's a typo actually. So a correction from the last lecture. So last time I wrote z plus w whole bar as z bar and w bar. This is not correct. You need an addition here. So this is the correction. Let me now give few exercises as homework. So this exercises. 1. Prove that mod of z plus w is less or equal to mod z plus mod w for all zw complex number. So the triangle inequality. Prove that the triangle inequality and discuss the case where equality holds. And discuss the cases when the equality holds. Alright. Now, next thing is one more exercise. So prove that mod of z minus w by 1 minus w bar z is less than 1 whenever mod z is less than 1 and mod w is less than 1. And then what happens when you allow equality also? But then there is an exception. This z bar w cannot be 1. Otherwise, there will be a 0 bar, something by 0 bar. Those we don't want. When this equal to and z w bar not equal to 1. Okay, so this two exercises. Alright. So last time I said that we'll go into power series, but I thought let me explore a little more about the inner product. Alright. So what I wrote the inner product as z w bar. This was our definition. Right? Now, of course, here Cauchy-Schwarz inequality become an equality, but now let us define an inner product zw over R. So I mean an inner product with respect to the real field. Inner product in C with respect to the real field R. So this one as real part of zw. Clearly this is real linear map in z and w both variables. There is no problem in that. And this z and z is real part of mod z square z bar, which is mod z square, which is equal to 0. So positive definiteness also follows. So, and ZW well, WZ R, this is what real part of W Z bar, which is also real part of W Z bar, which is real part of Z W bar. Alright, so which is ZW. Right, so since it is over real variable, it's symmetric. It's not conjugate symmetric now anymore. Alright, so this is an inner product on C over the field R, over the field R. Alright, now let us look at what exactly is this ZW. So ZWR is nothing but real part of ZW bar. Now if we put Z as x plus iy and w as u plus iv. So put this two and see what happens. So this is real part of x plus iy times u plus iv bar. Right. So now look at this one, x plus iy and u plus iv bar, which is what? Which is x plus iy times u minus iv. So which is nothing but xu plus yv plus I times yu minus xv. So this is the real part. So real part of ZW bar is xu plus yv. xu plus yv. Well, so this now note that if you consider C to be just R2 and x plus iy be as x comma y, then if you look at the inner product x comma y and u comma v in R2, this is the standard inner product in R2 is nothing but xu plus vy, and which is the same, which is nothing but this real part of ZW bar. Alright, so this is this clear? Yeah, so this must be clear. Right, so this real part is the standard inner product in R2. Now in this case, of course, Cauchy-Schwarz inequality will give you as this ZW R less or equal to mod Z mod W for all ZW in C. And this is not an equality now. This is a valid inequality. It's not necessarily equality all the time. So it will be equality when this Z and W are a real multiple of each other. But now what does it mean? It means this in real coordinates in R2 it means mod of XU plus YV is less or equal to square root of x square plus y square and square root of u square plus v square. Alright, this is the same thing. This is equivalent. Alright, here z equal to x plus iy and z equal to x plus iy and w equal to u plus iv. Right? Now maybe I can give a proof of this one. Yeah, so proof for this one, proof of Cauchy-Schwarz inequality. Well, you consider a different function. So generally the proof of inequalities start from a different stuff, different things. So there is always some kind of tricks. So you consider this function f lambda as x minus lambda u whole square plus y minus lambda v whole square, and we want to find the minimum of this function. This is of course greater equal to 0, right? Now you see here, if you want to find minimum, see generally this is one variable function, x, y, u, v all are fixed. So now we want to look at the first derivative and equate to 0. Find the point actually where the minimum of f exists. So I find lambda, this is, you just evaluate it first, x square minus 2 lambda xu plus lambda square u square plus y square minus 2 lambda y v plus lambda square v square. So here this goes away and here 2 xu and here yv comes in, lambda with respect to derivative, and here it is 2 lambda u square plus v square. So f prime lambda 0 implies lambda equal to xu plus yv minus u square plus v square. So you assume this, assume u square plus v square is not equal to 0. If it is 0, then equality is trivial. This is inequality and it is trivial. So not equal to 0, I assume. And here you see what value it takes. Take the second derivative with lambda. What you get is 2 times u square plus v square, which is positive. So this implies f has a minimum at lambda equal to xu plus yv by u square v square. Now evaluate it on that one. So this f of xu plus yv by u square plus v square is also greater or equal to 0. Now this gives us the following. Right, so now this becomes as, so f of x u plus y v by u square plus v square comes as, we look at the second line here, so x square plus y square is 0 minus 2 lambda, lambda is this one, xu plus yv by u square plus v square, and then this is xu plus yv plus 2 lambda square u square plus v square. So lambda square is xu plus yv whole square by u square plus v square whole square into u square plus v square. Alright, this one, this and this. Now this as x square plus y square minus, see here 2 xu plus yv whole square by u square plus v square minus xu plus yv whole square by u square plus v square, right? So this gives you that x square plus y square minus xu plus yv square by u square plus v square, and this is greater or equal to 0. This implies xu plus yv whole square is less or equal to x square plus y square times u square plus v square. Alright, so this actually proves Cauchy-Schwarz inequality. Alright, almost take the square root and we're done. Alright, so this gives a proof of Cauchy-Schwarz inequality. Next we look at few motivation behind considering the inner product, standard inner product. Okay, so maybe what we do is we look at the motivation for the inner product ZW equal to ZW bar the next video. Okay. Thank you.